In the silent, dark void of space, there is a music playing. It's a symphony not of sound and air, but of reality itself. A song conducted by the most powerful and mysterious objects in the universe, black holes. Today, on G-Fun Facts Online, we're tuning our cosmic radio to listen in. We're exploring the field of quantum acoustics, a science dedicated to decoding the songs of black holes to understand the fundamental laws of our universe. These melodies, which travel for billions of years as gravitational waves, aren't just strange space sounds. They are a direct line to the heart of Einstein's greatest theories and a whisper from the bizarre quantum world. So how can a black hole, an object that famously swallows everything, even light, possibly sing? The answer lies in the very fabric of the universe. Albert Einstein taught us that space and time are not a fixed, empty stage for events to play out on. Instead, they are a dynamic, interwoven fabric he called spacetime. Massive objects, like planets and stars, bend and warp this fabric, and that curvature is what we feel as gravity. Think of it like a bowling ball placed on a trampoline. The canvas sinks under the weight, and any smaller marbles rolling nearby will curve towards the bowling ball. That's gravity. But when something truly cataclysmic happens, something on an almost unimaginable scale, like two city-sized objects each 30 times heavier than our sun, smashing into each other at half the speed of light, they don't just bend space-time. They send colossal ripples surging through it. These are gravitational waves. For almost a century, these waves were just a prediction, a beautiful but unproven phantom in Einstein's equations. But that all changed on September 14, 2015. On that day, two massive L-shaped detectors with arms 4 kilometers long felt a tremor. These detectors, one in Louisiana and one in Washington State, form the Laser Interferometer Gravitational Wave Observatory, or LIGO. They work by splitting a laser beam and sending it down each arm. The beams bounce off mirrors and recombine. Normally, they cancel each other out perfectly. But if a gravitational wave passes through, it stretches and squeezes spacetime itself, minutely changing the length of the arms. The laser beams no longer cancel out perfectly, creating a signal. The vibration LIGO detected that day was impossibly small, a distortion of spacetime smaller than 1/10,000th the diameter of a proton. But it was unmistakable. It was the signal from two black holes, 1.3 billion light-years away, in their final, violent dance. To make this cosmic event understandable to our human senses, scientists translated the gravitational wave signal into a sound wave. The process is called sonification. And what did it sound like? A chirp. Imagine the sound. As the two black holes spiral closer and closer, they move faster and faster, whipping around each other hundreds of times a second. The frequency of the gravitational waves they emit skyrockets. This creates a rapid rise in pitch and volume, a crescendo that ends abruptly at the moment of collision. For the first time, as Caltech physicist David Wright said, the universe has spoken to us with gravitational waves. That chirp is the dramatic opening act, but the main performance, the part that holds the deepest secrets, begins the instant the two black holes merge into one. The new, larger black hole isn't born perfect. It's distorted, wobbling, and unstable from the violence of its creation. To settle down into a stable, spherical shape, it needs to shed this excess energy. It does this by vibrating, almost exactly like a bell that has just been struck, rings out with a clear tone. This phase is called the ring down, and as the black hole vibrates, it radiates its own unique pattern of gravitational waves. This isn't just random noise. The vibrations happen at a very specific set of frequencies and decay rates, which scientists call quasi-normal modes, or QNMs. You can think of these QNMs as a black hole's unique musical fingerprint, or its signature tune. Each note, and how quickly it fades away, tells us something fundamental. Here's why this is so incredibly important. A famous idea in physics called the no-hair theorem predicts that a black hole is shockingly simple. Imagine you bake a cake. The final cake's taste, texture, and appearance depend on the ingredients you used: flour, eggs, sugar, maybe chocolate or vanilla. But a black hole is like the ultimate cosmic oven. The no-hair theorem says it doesn't matter what you threw in, whether it was made from giant stars, neutron stars, or a collection of old spaceships. Once it settles, the final black hole has no memory of its past. It has no hair. It can be completely described by just three properties: its mass, its spin, and its electric charge. That's it. The theory states that the frequencies of the ringdown, those musical notes, should depend only on the final black hole's mass and spin. So by listening to this ringdown song and analyzing its notes, we can directly test if Einstein's theory of general relativity holds up in the most extreme environment imaginable. We can ask the black hole directly, "Are you really as simple as the no-hair theorem claims?" It's a profound test of our understanding of gravity. Listening to the cosmos is one thing, but what if we could bring a black hole into the lab? Not a real one, of course, but a perfect analog. This is where the story takes a turn from astrophysics to quantum mechanics, into a field called analog gravity. It has led to one of the most brilliant concepts in modern physics, the acoustic black hole. Sometimes called a sonic black hole, or, wonderfully, a dumb hole, because it traps sound or is dumb, not light. Let's go back to that river analogy. Imagine a river that starts off flowing slowly, but its speed gradually increases as it goes downstream. Now, imagine you're in a boat on this river, and you can shout. In the slow-moving part of the river, the sound of your voice travels both upstream and downstream. But what happens when the river's current becomes faster than the speed of sound in the water? You've now crossed a point of no return, a sonic event horizon. Any sound you make from this point on will be swept downstream by the current, unable to travel back upstream against the powerful flow. This is a perfect analogy for a black hole's event horizon, where the gravitational pull is so strong that the current of spacetime itself flows inward faster than the speed of light. Scientists have actually built these acoustic black holes. They use something called a Bose-Einstein condensate, a bizarre and fascinating state of matter where millions of atoms are cooled to just a fraction of a degree above absolute zero, minus 273 degrees Celsius. In this extreme cold, the atoms stop behaving like individuals and coalesce into a single quantum entity, a superfluid that flows without any friction. By using lasers and magnetic fields to manipulate this superfluid, researchers can create a region where the fluid flows faster than the speed of sound within it, creating a perfect, controllable, tabletop acoustic black hole. This incredible achievement gives us a window into some of the most bizarre quantum phenomena predicted to happen at the edge of a real black hole, things we could never hope to see across billions of light years. So what are these bizarre phenomena we can now study? The first is perhaps the most famous prediction made by the late, great Stephen Hawking. In 1974, he stunned the world by showing that black holes are not completely black. By combining quantum mechanics with general relativity, he theorized that they should emit a very faint thermal glow. This is now known as Hawking radiation. The idea is that the empty vacuum of space is actually a fizzing soup of virtual particle-antiparticle pairs that pop into existence and then immediately annihilate each other in a flash. But if this happens right at the edge of a black hole's event horizon, one particle might fall in while the other escapes. From an outsider's perspective, the escaping particle becomes real, looking as if it has been radiated by the black hole. It carries energy away from the black hole, meaning that over unimaginable timescales, the black hole would slowly lose mass and evaporate. Actually detecting this radiation from a real black hole is practically impossible. A solar mass black hole would have a Hawking temperature colder than the background temperature of the universe itself, making it completely undetectable. But our acoustic black holes in the lab offer a way. The theory predicts that the sonic event horizon should do the exact same thing, but with sound. It should convert the quantum vacuum fluctuations in the superfluid into real, detectable sound particles, or phonons. It would be a phononic version of Hawking radiation. And amazingly, in 2014, scientists reported the observation of this effect, creating sound from the quantum vacuum in a lab. Another closely related idea is the Unruh effect. It states that if you were accelerating through what you thought was empty space, that vacuum would not seem empty to you. Your acceleration would make the vacuum's quantum fluctuations appear to you as a warm bath of particles. Again, this effect is far too subtle to measure by accelerating a detector through space. But in an acoustic black hole analog, a detector can be accelerated through the silent phonon vacuum of the cold atomic gas. If the theory is right, that detector should start to hear sound that is generated purely by its own acceleration. These lab experiments are our only real chance to confirm these deep, strange predictions that sit at the boundary between gravity and the quantum world. This brings us to the ultimate goal. Why do we listen to cosmic chirps and build sonic black holes in labs? It's all part of the grandest quest in modern physics, the search for a unified theory of quantum gravity. We have two incredibly successful theories of the universe. General relativity perfectly describes the large-scale world of planets, galaxies, and gravity. Quantum mechanics perfectly describes the small-scale world of atoms and particles. The problem is, they don't work together. In places where both are important, like the singularity at the center of a black hole or at the very moment of the Big Bang, the equations of these two theories break down and give nonsensical answers. Black holes are the perfect laboratory for pushing these theories to their limits. The precise details of the ring-down song from a merger could hold subtle deviations from what general relativity predicts, tiny imperfections in the music that could be clues pointing the way to a more complete theory of quantum gravity. Some physicists even wonder if spacetime's extreme curvature near a black hole could fundamentally alter the rules of quantum mechanics itself. Experiments are even being designed to see if Earth's own gravity, though weak, might be introducing tiny, non-linear effects into the quantum world. Listening to the songs of black holes is how we interrogate nature at its most extreme. While the chirps and ring-downs of gravitational waves are one type of black hole song, it turns out there's another, completely different cosmic sound. This one isn't a ripple in space-time. It's a true sound wave traveling through a medium, just like sound travels through air. Astronomers were studying the Perseus galaxy cluster, about 240 million light-years away. At the center of this cluster is a supermassive black hole, billions of times the mass of our Sun, and it is surrounded by a vast cloud of incredibly hot gas. Using NASA's Chandra X-ray Observatory, they saw vast concentric ripples or pressure waves spreading out through this gas from the black hole. These are, literally, sound waves on a galactic scale. NASA was able to translate these waves into a musical note. The result is the deepest note ever detected in the universe. It's a B-flat, but about 57 octaves below middle C. That's a frequency over a quadrillion times lower than what humans can hear, with one oscillation taking over 10 million years to complete. This deep, impossibly low hum is caused by the black hole periodically blasting out huge jets of energy, which creates powerful pressure waves that ripple through the cluster's gas like a cosmic drumbeat. It's a powerful reminder that black holes don't just passively swallow matter. They are active engines that profoundly shape and regulate the growth of their entire galactic environments. So the universe is anything but silent. It sings with the voices of its most extreme and enigmatic inhabitants. We're hearing the violent, chirping crescendo of two black holes spiraling to their doom. We're listening to the pure, ringing tones of a newly formed event horizon settling into a perfect sphere. We're detecting the deep, resonant hum of a supermassive black hole shaping its entire galaxy. The emerging field of quantum acoustics is our framework for interpreting this grand symphony. By listening to the gravitational wave signals from deep space, we are testing the very limits of Einstein's gravity and mapping the population of black holes across cosmic history. And by creating their acoustic twins here on Earth, we are experimentally probing the quantum weirdness of Hawking radiation and the Unruh effect, getting our first tangible hints of how gravity and quantum mechanics might finally unite. The era of listening to the cosmos is just beginning. As our detectors become more sensitive and our lab simulations more advanced, the cosmic symphony will only grow louder. Who knows what new melodies and deeper harmonies are waiting to be heard, and what secrets they will reveal about the fundamental nature of our universe. Thanks for listening.